Hello everyone. So now we're going to talk about the sign of a function. After the actual definition of the sign of a function, so when is a function zero, strictly positive or strictly negative, we will look at examples of looking for the sign of a function from the graph of a function. And of course, in that case, it's very straightforward. It's more like a labeling process. Like you just have to check when is the graph crossing the x-axis for the roots, when is it above the x-axis for the strictly positive parts, and when is it below the x-axis for the strictly negative part. But then the ultimate goal will be like if you have a function that is defined algebraically, so with an equation, how do you compute where a function is equal to zero, strictly positive or strictly negative? And this will be done using sign tables. So here we go. So let's start with the actual definition. So first, definition here, 1.4.5, we're talking about the sign of a function. So let f be a function and let x equal a be a point inside the domain of f. If the value of that function at a is equal to 0, we say that a is a 0 or root for the function. If the output at a is strictly bigger than 0, we say that f is strictly positive at x equal a. And if f of a is strictly negative, is negative, then we say, oh my god, it's strictly less than 0, we say that f is strictly negative at a. So let's start with an example where we're going to find the roots, the strictly positive part and strictly negative part on a graph. So first example here, let's find the sign of the function defined below. So the first thing we're going to do is, I like to find the roots first. So the roots of a function, when you have the function defined visually, so when you have the graph of the function, so we're looking for all x values that are such that f of those values are equal to 0. This corresponds visually where the graph intersects with, say, the x-axis. So here we have one root, so the graph of the function is crossing. So here at 0, the function is touching the x-axis. At that point here, it looks like that point could be maybe 1.6. As long as you have a number that makes sense, I don't really care. And then it also crosses here. Let's say it's around 3.8. I mean, if you say 3.7, as long as you're consistent, so I'm going to use 3.8, but as long as you're consistent, you're going to get full marks. Okay, so and normally on a test or in web work, you will see the roots a lot clearer, or they're going to be nice numbers. But anyway, so here, so the roots here, so we have 3 points, so boom. Okay, so f of x is equal to 0 at 0, 1.6, and 3.8. Now, what I like to do is just trace over and look at when is the branch positive and when is the branch negative. So here, if I start at -1, the function is equal to 37, and then it's positive all the way up to 0, so that branch is above, so this will be a positive part. After 0 until 1.6, the part of this graph here is going to be again above the x-axis, so it's going to be again positive, so it's positive between -1 and 0, between 1 and 2, but then, between 0 and 1.6, but then between 1.6 and 3.8, between 1.6 and 3.8, the function is going to be below the x-axis, so it's going to be strictly negative, and then after 3.8 all the way up to 4, we have a positive branch. So this means if you are writing up the positive side, so the function f is positive when boom, okay, between -1 and 0. So it's always with respect to x here, union between 0 to 1.6, union 3.8 to 4. Notice that it's including -1 because at -1 it's equal to 37, but it's not including 0, 1.6 or 3.8 because those are roots, but it's including 4 because it's strictly above the x-axis. And we have only one interval, only one interval, okay, that is below, boom, the x-axis where it's strictly negative between 1.6 and 3.8. So since we're there, might as well do it because this is how it's going to be done on the test. But if you are looking at the domain of this function, clearly this function is defined between -1 and 4. The highest spot, so the domain is going to be between -1 and 4. The range, the lowest possible value is -27. So let me just highlight what I'm talking here. So for x here, between -1 and 4, between -1 and 4. And then for the range here, I'm going to be between -27 all the way up to 37. And of course, you can draw this graph from the beginning until the end without lifting your pen. So actually the domain here is also the continuous domain. So as a remark here, so here we go, poof. So domain from -1 to 4, range from -27 to 37, and the continuous domain from -1 to 4. Everything is included. All right, one of the biggest tool in Cal 1, okay, so one of the biggest one is sign tables. So for us, all the functions we're going to study are going to be continuous. In particular for us, the functions that are going to interest us are going to be defined algebraically by a single equation. And this will guarantee that the function is continuous. So in other words, if you have an equation, if you have a function that is defined by an equation, and there's only one equation, and it contains only terms that you know very well, like rational functions, radical functions, algebraic functions, or exponential equations, logarithmic equations, and trigonometric terms. So if you have a big equation constructed from those guys, or those girls, or those people, if you compute the domain, automatically you know where it's continuous. And the steps that I'm going to go over, they work for continuous functions only. So what do you do to construct the sign table? So there's a couple of steps. The first thing that you do, is you need to find the points where the function is undefined, which separates two intervals where the function is defined. So if you have a function that crashes at 0, but it's defined before and after, 0 is one of those important columns that you're going to use inside your sign table. So you need to find those special points that separates the domain into pieces. The next thing you're going to do is you're going to find the roots of the function. So you want to know the sign of the function, which will include, of course, when the function is 0. And then you're ready. So the points that splits the domain and the points that are giving you zeros will be important columns. And these will be the first thing you're going to put in your sign table. And then you're going to check what's going to happen in between those undefined points and those roots. So what does it look like, the sign table? It will be a lot clearer with an example. I'm just going over the methods for now. So there's two rows. The first row is just labeled by X. And then what you put in that row are like you put the important columns coming from the undefined points and the roots. And then in between the undefined points and the roots, you're going to have intervals. And then the second row, which you label simply the sign of X, will contain one of the following 4 things. So if you have a point where it's undefined, you're going to put in the second row undefined. If you have a column where the X value is a root, you're going to put a 0. So for any interval in between these important points, the function is going to be either strictly positive or strictly negative. And the idea here, and this is the beauty of sign tables, you just need to pick one point. So you pick one point in the interval and you evaluate your function. And if you get something strictly positive, then boom, your function on the whole interval is strictly positive. And then if you pick a point on an interval and you get something strictly negative at that point, just for one point, boom, on the whole interval, the function needs to be strictly negative. That's really beautiful. Let's look at an example right away to illustrate this. Here we go with an example. Let f of x be equal to x minus 1 over x plus 1 times x minus 3. Let's construct the sign table. So the first thing you always do is you first find where is this function undefined. Okay, so here we just need to look at the denominator. When is x plus 1 equal to 0? And, or when is x minus 3 equal to 0? So of course, x plus 1 will be equal to 0 if x is equal to minus 1, and x minus 3 will be equal to 0 if x is equal to 3. So we have 2 points where the function is undefined. Of course, this corresponds to when is the denominator equal to 0. So 2 possibilities only. X is equal to minus 1 or x is equal to 3. So the function crashes at minus 1 and at 3, and that's it. So these will be 2 important points for us. Minus 1 and 3 are going to be 2 undefined columns. So what about the zeros? So this will correspond to when is the numerator, numerator equal to 0. So here, if I look at the numerator, I only have x minus 1, and x minus 1, of course, is going to be equal to 0. Is going to be equal to 0. So I'm just looking at the numerator here. If x, if x is equal to 1. So when is the numerator equal to 0? It's going to be equal to 0 if and only if x is equal to 1. So this will be another important column. So for us now, there's 3 essential ingredient, like our important columns here for our sign table: minus 1, 3, and 1. So when you construct your sign table, of course, here I'm like a cook. Okay, I've already have my outline of my sign table. This is something that you need to do on your own. So I have a row for x, I have a row for sign of x, and then in that sign table, I construct 3 columns because I have 3 important points here: minus 1, 3, and 1. So the smallest one is minus 1, so I have 1 column for minus 1. Then the second one is 1, so I think about all 3 points here. And then the last one is 3. So it's really, really important that they are in separate columns with room in between, and they are in ascending order. And then we're going to wonder what's up before minus 1. Before minus 1, that's the interval from minus infinity to minus 1. What's up between minus 1 and 1? Well, that's the interval minus 1, 1. What's up between 1 and 3? Well, that's the interval 1 until 3. And then after 3, that's 3 to infinity. So you create the intervals in between them. So I like to start with my columns. Why is minus 1 there? Well, minus 1 is there because the function is undefined. Why is 1 there? Well, we have a root, so it's equal to 0. And why is 3 there? Because it crashes, it's undefined. And now what you need to do is decide under the interval for the second row under the intervals, is my function strictly positive or strictly negative? And here, this is the beautiful thing, because the function is continuous, you just pick 1 point. So for the first interval between minus infinity to minus 1, just pick 1 number. It does not really matter which one. I'm going to pick minus 2. It really does not matter if you compute the output. So you put minus 2 in your function. You can use a calculator to double check that. But if you put minus 2 in your calculator, you're going to get a number that is strictly negative. So the whole function will, the graph of that function is going to be below the x-axis. So it's negative. Between minus 1 and 1, well, let's pick 0. So if you plug 0 in your function, this one's kind of easier to compute. You get 0 minus 1 over 0 plus 1 times minus 3. So you're going to get something positive. So you can double check that f of 0 is positive. So the whole function is positive. For the full thing, even if I'm just choosing 0, it's positive everywhere. So this is not, you don't really need to show that. Okay, normally you just either do it on the calculator or whatever. Okay, as long as you understand how to compute the sign just by picking 1 point. Between 1 and 3, why not just 2 here? So if you compute the output at 2, you can double check that this will be strictly negative. So the function is negative throughout the interval 1, 3. And then after 3, again here, anything in a cloud or in a headless sheep here, I don't need to see this not necessarily on a test. So here and then after 3, let's pick 4. We don't need to go too far here. If you compute f of 4, you can double check that this is strictly positive just by evaluating your function. So the function is strictly positive after. And then that's basically it. Like, we know now that the function is 0 at 1 It's strictly negative between minus, let me just color this as I'm doing this, so it's 0 at 1. It's strictly negative between minus 1, between minus infinity and minus 1, and between 1 to 3. I have two intervals where it's strictly negative, and I have two intervals where it's strictly positive, so between minus 1 and 1, this is strictly positive, and between 3 and infinity, it's strictly positive. And what's cool is, and I have two follow-up questions here, and typically this is how a question could be assigned to you. Let's use a sign table to compute the domain of this new function. So I have a new function here. Okay, so a new function. And what I'm trying to do here is I'm trying to compute the domain of this new function, which is the square root of f of x. So the square root of x minus 1 over x plus 1 times x minus 3. And here, what you need to remember is that inside the square root, you can have like something positive or something 0, but strictly negative will crash. So here in your sign table, basically you just go and you pick what is positive and what is negative. So here, what is positive? So here I have one interval, sorry, what is positive and 0? So I have one positive here, 1 0 here, that's going to work out, and one positive also here. So when I'm computing the domain for G, I'm going to start at minus 1 all the way up to 1, but now I'm going to include 1 because 0 is accepted. And then I'm going to glue the last interval, 3 to infinity. I'm not including 3 because it's undefined there. And now suppose I'm again curious and I have another function, but now it's the ln of x minus 1 over x plus 1 times x minus 3. Now inside a logarithmic function, what you need to remember is you can only have pluses. So if you can only have pluses, so this means here you only keep the pluses now. So let me use, so here I'm going to keep the pluses. So this is a plus. I don't care about the 0 anymore. And I have a plus here. So I'm going to only have two intervals for the domain of h. So the domain here for h. So I only keep the pluses in the sign table. So it's from minus 1 to 1, union 3 to infinity. So basically now that 1 is excluded because at 1 we get 0 and none of 0 is bad. Okay, so only the pluses for the domain of ln of something. But for the square root, it's pluses or zeros. All right, let's do another example. Let's go right away to the last example. We have f of x is equal to x minus 1 over squared over x squared minus 9. So sometimes there's a bit of preliminaries here before you do these things. So x minus 1 squared is already factored as x minus 1 squared, but down there, x squared minus 9, that's the difference of square. So it's the same as x plus 3 times x minus 3. So when you're constructing the sign table, the first thing you want to do is check where does it crash. So it will crash when x plus 3 is 0 or when x minus 3 is equal to 0. So that will happen when x is minus 3 for the first bracket or when x is equal to 3 for the second bracket. And then for the root, you just need to look at the denominator. So here when is x minus 1 equal to 0, that will happen when x is equal to 1. So for undefined, we have x minus 3 or x equal to 3. And for 0, when is it 0? That's when x is equal to 1. So three important points again, minus 3, 3, and 1. You put them in ascending order. So 2 rows for your sign tables, 1 row for the x's, 1 row for the sign of f of x. So the first important column, always leave room here for the before and after the first column. So the first column here will be minus 3. The reason why minus 3 is there because the function is undefined. And then we have 1. The reason why 1 is there because we have a root. And finally we have 3 because the function is undefined. Now we need to check before minus 3. That's between minus infinity to minus 3. In between minus 3 and 1, that's the interval minus 3 to 1. And then in between 1 and 3, that's the interval 1 and 3. And then after 3, which is 3 to infinity. And now we need to figure out the sign before minus 3, between minus 3 and 1, between 1 and 3, but just by picking one point everywhere, we're going to, on every interval, we're going to be able to do that. So here you don't need to write that down, but I am going to do it for the sake of completeness. So if I pick minus 4, you can double check. Okay, you can double check that this function is actually positive at minus 4. Between minus 3 and 1, let's pick, let's say, 0. Okay, so if you compute f at, just realized that for a little mistake here. I just wanted to have, it's not f of x, I want to write f of minus 4. Okay, sorry. So here f of 0 is going to be negative. This one is always easier to see. 0 minus 1 is minus 1 squared, it's positive. 0 minus 9 is negative, so we have negative here. So between 1 and 3, let's pick 2. You can double check that at 2 the function is negative still, so negative. And then f for after 3, let's pick 4. F of 4, you can double check that this is positive. Again, this is just to show you how I got the plus and the minuses. So I'm not really doing the computation here, but normally you use a calculator, you plug in minus 4, you plug in 0, you plug in 2, you plug in 4, you look at the output. If it gives you 7.5 something, okay, that's a positive number, you put a plus. If you get minus 17.2, well, you just put a minus. You don't care about the actual output, just the sign, okay, and that gives you the sign for the full interval. So that's your sign table. So again, here a lot of information. We just from the sign table, we know it's 0 at 1. We know there's a branch above the x-axis between minus infinity to minus 3, and there's another one between 3 to infinity. And then there's 2 branches below between minus 3 and 1 and between 1 and 3. And then a typical question, again here, it's very similar to the previous thing. So if you have a new function, which is the square root of the previous one, and you're asked to compute the domain that you have to do, and this is very, very typical. The question could just be, A, use a sign, compute the domain of the square root. It'd be up to you to click, I need to go inside and compute the sign. And for the square root, you need to remember, okay, that you're going to just keep the plus or the zeros. Okay, so it's pluses or zeros that you keep. So in the sign table, if I go and I seek my pluses, so I have a plus here, and I have a 0 here at 1, and a plus after 3. So this means that the domain of G, so if I glue everything together, so the first interval is from minus infinity to minus 3. Don't keep the minus 3, it's undefined there. The square root is not going to resuscitate that minus 3 back to life. Okay, so then there's only one alone, like me. Okay, so here, union 1. When it's alone, you're using curly brackets, and then the last interval where it's positive, it's 3 to infinity. So you just keep the pluses and the 0. That gives you the domain of G. And then for the last question, if you're asked to compute the domain of ln of f of x, then you're just going to keep the positive ones and not the 0. So I have a positive here and a positive there. So you just keep these 2 intervals to create the domain of h. So domain of h here. So you get from minus infinity to minus 3. Not keeping the 1 anymore, union 3 to infinity. And that's your domain for h. So again here, so for C, okay, so for C, or in general, the question could simply be compute the domain of ln of some big shit. Okay, you just say, well, let's find the sign table of that shit, and let's just keep the positive part. If you have the square root of some shit, let's construct a sign table of the inside and keep the pluses and the zeros, okay? So very important question B and C, because on a test it could simply be like that. Okay. All right. For sign of continuous function. That's it. Bye-bye. That's the end of chapter 1. Super. Bye-bye. Oh my God. Bye.